Okay, so we've officially made it to the start of actual physics, and let's start by laying down the roadmap for sections 1.7 and 1.8. Now we're going to start off with section 1.7, which is all about vector addition and subtraction. And we're first going to define two terms, and those are scalar quantities and vector quantities. And then we're going to move on and talk about vector addition and subtraction, and we're going to cover the commutative law and the associative law for vectors. After that, we're going to work on an example problem, and we're going to test our understanding of section 1.7. Then we're going to move on to section 1.8, which is all about the components of vectors, which is one of my favorite things to learn because it's extremely useful. We're first going to cover how to actually find the components of vectors using diagrams. We're going to define things like the cosine and the sine, and special notes about them. After that, we're going to work on an example problem, and then we're going to use components to do vector calculations, specifically covering three areas. Number one, how to find a vector's magnitude and direction from its components. Number two, what to do when multiplying a vector by a scalar. And number three, using components to calculate the vector sum of two or more vectors. Once we've covered those definitions, we're going to move on to an example problem, and then finally, we're going to test our understanding of section 1.8. So let's get started with section 1.7, vector addition and subtraction, starting off with the two definitions of scalar quantities and vector quantities. Now, we've actually already been working with scalar quantities. These are quantities defined by a magnitude and also a unit. What should be new here is a vector quantity. Now we're going to define a vector quantity as a quantity defined by a magnitude and a direction. But first, let's give you some examples of scalar quantities. These are things like mass, things like speed, things like temperature, things like time. They only require the number, the magnitude, 75, and then the unit, kilograms. Or maybe someone is moving at 8 meters per second. Or maybe it's 75 degrees Celsius. All that you need is the magnitude and the unit. A vector quantity, however, needs a magnitude and a direction. So let's look at an example. Our first example that we're going to cover is displacement. Displacement is one of the easier vector quantity examples. Now, we're going to define displacement as the change from final to initial position. Actually, the change from starting to final position. Now, I want you to pay really close attention to this definition, specifically three parts. It's talking about a change, okay? Keep that in your head. And it's only talking about the starting to the final position. Remember that. We're going to cover that later, but it's really important. So let's do an example. Let's say I'm standing here, and this place is my house, this little dot, and I want to move 5 meters, the magnitude, east. So let's do our little compass bearings. I moved 5 meters east. This thing that I've drawn, the yellow line with the arrow tip, is a vector. And let's call this vector A. And we know this is a vector because we're going to place an arrow on top. And another way you might see this is with the half arrow on top. This is how you draw vectors. You draw an arrow, place a letter, and you put another arrow on top. All of these are simply vectors. Now, I'm going to give you a pro tip about displacement. Remember when I said that displacement is just the change from the starting to the final position? Well, that's synonymous with saying displacement only cares about your final and starting points, not with how you actually got there. And you might be thinking, well, what does that mean? Well, let me show you. Let me show you. So let's say I was here and I walked 5 meters northeast. That's my displacement. But let's say I actually didn't walk that straight of a line. Let's say my actual path looks something like this. It's all jiggled up, went inside, came back here a little bit, I passed the mark, then I decided to come back and went here. This is what we call the actual distance traveled. This is the actual path that I took. But displacement only cares about this starting and this final point. Displacement and distance traveled are two very different things. So let's highlight that for a second. The distance and the displacement. Your total distance travel is going to be a scalar quantity, and it is path dependent. That means that it actually cares about the actual path you took. Displacement is a vector quantity, and it is path independent, meaning it doesn't care about the actual path you took, just the starting and the end points. So those are two very important things to keep in mind. And lastly, another thing we're going to define is the magnitude of a vector. The magnitude of a vector we're going to see illustrated with these absolute value bars. This is the magnitude. Whenever you see the absolute value bars enclosing the vector, you know that you're talking about magnitude. So let's move on to vector addition and subtraction. So in this section, we're mainly covering two things, and those are the commutative law of vector addition and the associative law of vector addition. Now, what are those exactly? Well, let me show you. The commutative law simply states that when you add two vectors, such that C is equal to A plus B, and remember, these are vectors, well, that's the same as saying C is equal to B plus A. The order doesn't change the end result. And let me prove that to you. Let's say that this is vector A and that this is vector B. Now, whenever you add vectors, look at what I just did here. I placed the starting point of vector B at the tip of the arrow of vector A. That's how you add vectors. And to show the result, you go from the starting point of your first vector to the end point of your second vector. That is vector C. Now let's try it the other way around. Let's say we have vector B, and then we add vector A. Now this gets us vector C. Remember, this is A, this is B. And as you can hopefully see from my basic drawing, these two vectors are the same. It didn't matter which order we added them, vectors A and B, we got the same answer. And that's the commutative law. Now, let's talk about the associative law, which in my opinion is just a branch from the commutative law itself. So hopefully it won't be too hard to understand. Let's say we have C plus B parentheses plus A. The associative law states that this is the same as saying C plus parentheses B plus A. So essentially what this is doing is it's doing the same thing. It's switching up the order in which we're adding things. So let's prove that visually. Let's go ahead and prove this one as well. Let's say we have our three vectors here. this one's going to be C, this one's going to be B, this one's going to be A. And let's try to prove the left-hand side, which is C plus B, and then the result of that plus A. So let's label this C plus B, and then the result of that plus A. Okay, this is C plus B, parentheses, plus A. Okay, and that's what it looks like. Now let's prove the left-hand side. And of course, guys, my diagrams won't be exactly the same, but I think it'll be close enough to where we can understand the message. Remember, left-hand side starts with B plus A, and then it's C plus B plus A, C plus B plus A. Now, of course, these two arrows aren't exactly the same, but that is simply because of my lack of drawing skills. But hopefully you can see how, if the diagrams were actually to be accurate, that those two depictions would be equivalent. And that is the commutative law and the associative law of vector additions. And now let's move on to an example problem. Okay, so we're going to cover example 1.5, having two vectors at right angles. And this states that cross-country skier skis 1.0 kilometers north and then 2.0 kilometers east on a horizontal snowfield. How far and in what direction is she from the starting point? Cool, so I went ahead and I drew a little diagram here. So you can see we have our compass bearings, northeast, salty waffles, and this is the first path she took, 1 kilometer north, followed by 2 kilometers east. Now we want to know how far and in what direction. So we want to know the magnitude of this vector here and in what direction it's pointing in, which I sort of defined by the theta. Now, how far is relatively easy because all we need to do is remember the Pythagorean theorem, which is C is equal to A squared plus B squared. In this example, C is simply our question mark, and that is equal to 1.0 kilometers squared plus 2.0 kilometers squared. Now, this is simply the square root of 5 with kilometers. And the square root of 5 is going to give us a decimal answer that we round down to 2.24 kilometers. And it is 2.24, remember, because of 3 significant figures that we have in both are factors. Always remember those significant figures, guys. Okay, so cool. So we got our magnitude, the how far, to be 2.24 kilometers. Now we need the direction. The direction, we're going to have to use a little bit of trigonometry. So if you remember, tangent of theta is defined by opposite over the adjacent side. In this example, that is simply 2.0 kilometers and divided by 1.0 kilometers, as you can see from the diagram there. Hopefully that's not too hard to imagine. So now we need to isolate theta, and we do that by taking the inverse tangent of both sides, and I simply let them cancel out. On the left-hand side here, I didn't write them, but that's our equation for theta. Now, if you simply plug this into the calculator, like I'm about to do, you get that theta is equal to 63.4 degrees. Okay, but now we need to actually label that as a direction and the northeast salty waffles. We know that this angle is 63.4 degrees. Another way that we can say this is that she traveled 2.24 kilometers at 63.4 degrees east from north. Because remember, this angle is going from north to east. And this would be the answer to our problem. So now let's move on to testing our understanding of section 1.7. Okay, so this is the test for understanding of section 1.7, and it goes like this. Two displacement vectors S and T have magnitudes of 3 meters and 4 meters respectively. Which of the following could be the magnitude of the difference vector S minus T? And here are our options. 9 meters, 7 meters, 5 meters, 1 meters, 0 meters, and -1 meter. Okay, now I actually really like this problem because it's going to teach you quite a little bit of things and it's going to reinforce some ideas that are important to know. So what we're first going to do is we're going to take away the options that simply don't make sense. And we're going to start off with, and the first one we're going to cover is -1 meters. And maybe this might not come intuitively to you, but this is wrong because magnitudes have to be greater than 0. I wrote that wrong. Magnitudes have to be greater than 0. A magnitude can only be positive. It would be akin to you asking someone, how far did you walk to get to your house, to the store? And they say, oh, I walked a total of -5 meters. And you just think to yourself, how can you walk a negative number? It doesn't make sense. As a magnitude, negativity doesn't make sense. In directions, negativity does make sense, but we're talking about magnitudes here. So it doesn't make sense. So right off the bat, option 6 is gone. Now let's talk about option number 5, 0 meters. Now, when we're performing either subtraction or addition, we need to keep in mind the magnitudes. And in this case, we have magnitudes of 3 meters and 4 meters. Now, I'm going to change it so that instead of reading simply subtraction, we're reading addition of a negative exponent. Now, when you're adding two vectors, there are two requirements that they must meet in order for their magnitude to equal to 0. Number one, their magnitudes are equal. And number two, they are anti-parallel. So for example, if you have these two vectors, as you can see, equal magnitudes and anti-parallel, they would cancel out. Now, if you had these two vectors, equal magnitude, but in completely opposite direction, when you add them together, they will not cancel out. There will be this x component here that does not cancel out from this vector. So we accept those two to be the requirements. Based on requirement number one, that their magnitudes are equal, in our case, 3 meters and 4 meters, we can simply rule this out based on condition number one. Since the magnitudes are not equal, we know that they cannot possibly add up to be a 0 magnitude vector. I hope that made sense. If it doesn't, please feel free to ask in the comments for clarification. Now, we're going to jump over to option number 1, 9 meters. Now, 9 meters, think about it. How can we get 9 meters from 3 meters and 4 meters? How can we get 9 when we only add 3 and 4? Even if we were to connect these two vectors so that we obtain the highest amount of magnitude in the resulting vector, which is pretty much just from the end of one to the tip to another in a straight line. Even if we add them to the most highly possible resultant, that only gets us 7 meters. So 9 meters is out of the question because we simply cannot achieve that level of magnitude from these two factors. But what we did learn here is that when added in a specific straight way, we actually are able to get option number 2, 7 meters. And that is that the vectors are simply in a straight line. Now, let's move on to discussing option number 3, 5 meters. How can we perform the following addition of vectors such that we get 5 meters? Well, when you see the numbers 3, 4, 5, we're going to be trained to think of that as a triangle. To think of it as a triangle with a leg of 3 meters, an upward of 4 meters. I'm going to draw that better. And it leads to the final 5. That's actually a triangle. So let's say this is S, and let's say this is negative t, and a resultant is this vector c with magnitude of 5. This is completely possible, and all we need to do is check using Pythagoras' theorem of c squared is equal to a squared plus b squared. And let's see. So 5 squared is 25, 3 squared is 9, 4 squared is 16, and as you can see, 25 does indeed equal 25. So if our vectors were added in such a way, then it is completely possible for 5 meters to be a resultant magnitude. Cool. What about 1 meter? Let's say that we have our vector of 3 meters here, and we have our vector of 4 meters going in the opposite direction. Now, you should be able to see that because of this difference, it would be completely possible for us to get a vector with a 1 meter magnitude, depending on how we add them. So that's actually all we need to know to show that option 4 could be a possibility. And that's going to be the solution for this section of 1.7. And now we're going to be moving on to section 1.8, which is all about the components of vectors. So let's start off by drawing a vector. And what we're going to say is that this vector is made up of its 2 legs, right? Now, it is important that you understand that these legs are not vectors. These are just components. They will be vectors later on, but for now, think of them as simply components. Now let's label this vector A, and this is going to be the x component, and this is going to be the y component of vector A. Now, we're going to use a bit of trigonometry to help us find out what these components are. So as you know, cosine of theta is equal to the adjacent over the hypotenuse. Now, look at this definition. We're talking about the magnitude of A. So this triangle, you can simply imagine to be a triangle of magnitudes. AX and AY are magnitudes. They're not vectors. These are scalar quantities, and the magnitude itself is also a scalar quantity. So with that in mind, let's continue. We also know sine theta is the opposite over the hypotenuse. So we rearrange these specifically by multiplying the magnitude of A to both sides. We get the following. And this is going to be our working definition for the components of a vector. AX is equal to the magnitude of A times cosine of theta, and AY is equal to the magnitude of A times sine of theta. And now, let's discuss a pro tip. These definitions will only always work, like these exact ones will always work so long as theta is defined counterclockwise from the positive x-axis. So theta has to be an angle that goes in said direction, which I guess I should kind of fix my picture to go like that. Theta has to be counterclockwise from the x-axis, and these definitions will always work. Now, you will see me solving problems in a different way using different angles. I do so because it is possible to still use other definitions of theta while using the trigonometric identities. You simply have to pay attention to where you are looking, which quadrant you are in, and which angles you are using. But we're going to talk about that later on. Right now, let's actually work on our first example problem. Okay, so here we are at example 1.6, finding the components. And it goes like this. It's a two-parter, but we're going to focus on part A for now. And that is, what are the x and y components of vector D? And as you can see already, the textbook is giving us a vector in the fourth quadrant, and it's giving us an angle that is not defined classically, starting from the positive x-axis and going counterclockwise. Instead, we get an angle, alpha, defined as 45 degrees clockwise from the positive x-axis. So, there are a few different things you can do with this angle. I'm going to choose to do the following. As you can see, our x component is this section here, and our y component is this section here of the diagram. Now, remember, I said I was going to do things a little bit differently. So I'm going to label what each component is, and I want to see if you can follow along. So dy is going to be equal to, classically, the magnitude, and in this case, it is going to be sine of alpha. Dx is equal to the magnitude times cosine of alpha. Cool. That shouldn't be too crazy to understand. It's pretty much what we just did. And now let's fill it in with our numbers. Okay. So you should be having a question here of, why did I use negative 45 degrees? Well, when the angle is clockwise from the x-axis, it's still okay to use these expressions so long as you use the correct angle. And in this case, that correct angle would be negative 45 degrees. However, an angle of negative 45 degrees clockwise is the same as saying an angle of 315 degrees counterclockwise. And all I did there was say 360 degrees minus 45 degrees is equal to 315 degrees. These two angles are the same, and if you wanted to, the official way, the classical way of solving this problem would be using the angle of 350 degrees, because it is counterclockwise from the positive x-axis, which is our classical definition. So you could substitute the angle there if you'd like to. It's the same thing, so I just prefer to do it the shorter way. And when you plug this into your calculator, you will get the following values. Okay, so as you can see, dy is a negative 2.1 meters, and dx is 2.1 meters. Now, important thing to note, we got the same number, even though sine and cosine are different. So this is actually an important property that's useful to keep in mind. Sine of 45 is equal to cosine of 45. And the same is true of their negative angles. Sine of negative 45 is equal to cosine of negative 45. And in general, sine of any angle theta is equal to, actually, not any angle. I almost really messed it up. When the angle is 45 degrees, these values are going to be the same. Either 45 or negative 45, they're going to be the same. Now, another important thing to note is the amount of sig figs we used. Because remember, since this angle only had accuracy up to 2 significant figures. Despite the 3 significant figures and the 3.0 meters, we use the lowest amount of significant figures, which is 2. Okay, so that's our answer for part A. Now let's move on to part B. Okay, so here we are, part B. What are the x and y components of the vector E? And what I really like about this problem is that it's doing something that you will see physics will do to you eventually, and that is that it's going to give you a little weird diagram. It's going to give you little weird axes just to make you think a little bit. But as you can hopefully see, this is still our standard diagram, just flipped around a bit. This is the positive x-axis, and this is the positive y-axis. So this vector is in quadrant 1. It just looks a little bit differently. But let's go ahead and solve this. So we want to find the x and y components. So as you can hopefully see, this right here is going to be the x component. And actually, I guess technically it'd be this. And this right here is going to be our y component. Now, I'm going to use angle beta to solve this because it gives this to us as 37.0 degrees. It's just that our trigonometric identities are going to look a little bit different. So EX is going to be equal to the magnitude of E times, and in this case, it is going to be cosine. I already messed it up. It's going to be the sine of beta, and dy is going to be the magnitude times the cosine of beta. And hopefully you can see that from the diagram, because the sine of beta is the opposite, this right here, which in this case is the x component. And likewise, the cosine of beta is the adjacent side, which in this case is the y component. It all depends on how the angle you are using is measured. Now let's go ahead and substitute in our values. Remember, guys, in this case, we are using an angle with 3 significant figures. So make sure to include that in not only throughout your steps, but also in your final calculation. So when you plug these values into a calculator, you're going to get the following answers. Okay. So we got 2.71 meters for our x component and 3.59 meters for our y component. Now, I want to talk about one slight drawback from the way that I'm solving these problems, and that is that had we received a problem in the following, in which we were given a vector in the third quadrant and an angle like this, when I were to solve for the x component and the y component, this angle is actually, I would always put it in as like a positive angle, like sine theta. However, this will almost always give me a positive answer. So for example, let's say I was doing the following calculation. Bx is equal to b of sine of theta. If I were to put this with actual numbers into a calculator, this answer would be greater than 0. Now, this is troublesome because I know that since this vector is in the third quadrant, that bx is actually less than 0. Like, I know that, just visually. So, in my method of solving problems, what I actually always need to keep in mind is to put this negative sign here. I need to do that because of the way that I like to solve problems. However, if you were to do the classical definition of an angle, for example, let's say in order to solve this problem, I calculated the angle all the way from the positive x-axis to the vector, and let's call that phi. If I was to solve this problem using the classical angle and the classical definition, p of x would look like this, and I actually wouldn't need to include this negative sign because the classical definition will always get you the correct sign and the correct magnitude. So that's just one thing, super important to keep in mind. And now let's move on to the next subsection, which is using components to do vector calculations. So in this section, we're going to cover 3 areas, and that is, number 1, finding a vector's magnitude and direction from its components. Number 2, multiplying a vector by a scalar. And number 3, using components to calculate a vector sum. And these are pretty much just definitions we're going to cover. So let's start with number 1. When we use magnitude, this is something we've actually already covered before. The magnitude of a vector is equal to its components squared, added to one another, and then under square root. That's just simple Pythagorean theorem applied to a vector. This is the magnitude. Now let's talk about the direction, which we've actually already done. And that is simply the identity that theta is equal to the inverse tangent of the opposite over the adjacent. In this case, that would be a of y divided by a of x. Simple things. We've slightly worked with them, and we'll work with them some more. Now let's go to section 2, multiplying the vector by a scalar. That's simply to say that if we take a vector r and we multiply it by a number, like let's say c, and let's say c is 5, so we have 5 times r, it would be the same as applying 5 times r of x and 5 times r of y. This is to say that when you multiply a scalar to a vector, you also multiply that scalar to its vector components. And now, there's actually a better way to illustrate this example, but in order to do that, we need to introduce unit vectors, which we will do so in section 1.9. But for now, I hope that is slightly understandable. Let's move on to section 3, using components to calculate a vector sum. And that's very similar to what we just said. Let's say, for example, we had r is equal to vector a plus vector b. This is the same as saying that r of x is equal to a of x plus b of x, and r of y is equal to a of y plus b of y. Now, this may sound like very simple things, but this is actually extremely powerful, because what I just said, what we just wrote down, was basically that the x component of your resulting vector is equal to all the x components of your additive vectors added together. Something like that. The y component of your resultant vector is just all the separate individual y components of the vectors you're added together. Extremely, extremely powerful definitions we're working with here. And we'll sort of reinforce this idea later on. For now, let's work on an example problem. Okay, here we are at example 1.7. Honestly, a really interesting and fun problem. And it goes like this. 3 players on a reality TV show are brought to the center of a large flat field. Each is given a meter stick, a compass, a calculator, a shovel, and in different order for each contestant, the following 3 displacements. You see vector A, vector B, and vector C. The 3 displacements lead to the point in the field where the keys to a new Porsche are buried. Like, how cool is that, a new Porsche? 2 players start measuring immediately, but the winner first calculates where to go. What does she calculate it? So basically what's going on is that there are 3 players. They each got these 3 displacements, but in different order, so that they're not all just doing the same thing. And 2 of them just started measuring, and I'm assuming digging, or whatever they're doing. But one of them was smart, and she said, okay, instead of just going step by step, displacement by displacement, I'm just going to figure out the final displacement path, and I'll just go there. That's what's going on. Now, let's solve this problem. And before we solve it, I'm just going to let you know, when I look at problems like this, I have a more mathematical mindset with vectors. A lot of people will draw out a diagram for these vectors, which, nothing wrong at all. I just want to let you know that that is not my style. I take a more mathematical approach, so I hope you can follow along, and I challenge yourself to see why the stuff that I'm doing makes sense. I'm going to start off by defining the x component and the y components of each vector. So it's going to look something like this. I know that for an angle that is east of north, the x component is going to include the sine. And if you can't visualize that in your head, I challenge you to draw out the diagram so that you can reinforce that idea, reinforce the ability to just see these angles mentally in your head without having to draw them. Similarly, for an angle 36 degrees south of west, I know that that is going to be a use of cosine, and I will not forget that negative sign there. Again, if you can't visualize that in your head, there's absolutely nothing wrong with drawing out a diagram. Before I calculate that, I'm simply going to write out the other components. Now, honestly, with these other components, I don't even think about it. I just do the opposite trigonometric identity of the vectors. So for example, if I know that the x component uses sine, therefore the y component is going to use cosine. I don't really think about that. Just sort of something I've come to realize with a lot of practice. And thankfully, the c vector is just one component, and that is the negative y component. It has no x component since it is just pointing south. Now, let's go ahead and get actual values for these. Instead of writing them here and having everything jumbled up, I'm just going to start a new line in which I organize everything. We already know the c vector pretty much, so let's just fill that in. Now, I'm going to go ahead, calculate everything, and once I'm done, I will be right back. Okay, so these are the final values that I got from my components. And now what we need to do is add up each respective x and y component so that we know the final x and y components of our resultant vectors. Now, in case you forgot, that is through the following formulas. We're going to call our final vector, our displacement vector, r, and this gets us that r of x is simply equal to a of x plus b of x, and r of y is equal to a of y plus b of y plus c of y, and I forgot the c of x here. But since there's no c of x, it's just going to be 0. So that is the same as 38.4 meters minus 46.4 meters and 61.4 meters minus 33.4 meters minus 17.8 meters. All of our answers are going to have 3 6 figs because thankfully every number in here is accurate only to 3 significant figures. And after I calculate this, I will be right back. Actually, important note, when I'm doing calculations, I keep the unrounded answers. Like here, you see me write 38.4 and negative 46.4, but in my calculator, I'm keeping the unrounded numbers just so that we get higher levels of precision, and we only round down to the actual sig figs at the very end. Okay, so you should have got something like this. The x component of your final vector is negative 7.99 meters, and the y component is 9.92 meters. Cool. Now what we need to do is to find the magnitude and the direction of this vector. So again, using our formula that we've learned, the magnitude is equal to its components squared. In this case, 7.99 meters squared plus 9.92 meters squared. Technically, I made a mistake. It's supposed to be negative 7.99 meters squared, but since it's a negative number being squared, it's always going to be positive. The displacement, the magnitude, like we've covered earlier, is always a positive number. And this gets you 12.7 meters for the magnitude. Part 1 of our solution. Now we need to find its direction, which we get using the formula with the inverse tangent. Now remember, this is the y over the x component, which I almost messed up, and it should look something like this. And this theta is actually going to give us a negative number. Now let's do a bit of thinking. We have a negative theta, we have a 12.7 magnitude, and we have our x components and our y components. So let's think a little bit. We know, like without even looking at any diagrams, x is negative and y is positive. R of x is negative, R of y is positive. So that's going to be a vector in the second quadrant. Now, since r theta is negative, that tells us that this angle is clockwise. So it's a vector in the second quadrant with a clockwise angle. That means that theta is going this way. So you can either define this new vector as a vector with 12.7 meters in the 51.1 degrees north of west, or you can use the classical angle, which we find simply using 180 minus 51.9, which is 128.9. But since we need 3/6 figs, this just becomes 129. So this is either a vector with magnitude 12.7 meters north, 51.1 degrees north of west, or 129 degrees from, oops, I forgot, counterclockwise from the positive x axis. Or you can even say this as 129 degrees north of east. It's just counterclockwise from the x-axis makes sense as this is an obtuse angle. So these two are going to be your solutions. This is the direction in which the winning participant went. Now, let's move to the last section of this video, which is testing your understanding of section 1.8. Okay, in this testing of our understanding, we have two parts. We're given two vectors A and B that lie in the xy plane. Can A have the same magnitude as B, but different components? And can A have the same components as B, but with a different magnitude? And let's start with part A. And the answer is yes. You can have components that are 3 and 4, which lead to a triangle with a hypotenuse of 5. And you can have a similar triangle with components -3 and -4, which similarly lead to a triangle with hypotenuse of 5. And that is how you can have the same magnitude as a different vector, but with different components. However, can you have a vector A with the same components as B, but with different magnitudes? And the answer is no, because if both of your components are 3 and 4, you will always have a hypotenuse with the magnitude of 5. If you have the same components for a vector, that is the same vector. You can't have the exact same components without having the exact same vector. So I hope that makes sense. I know I didn't give you something to visualize for part A, but that's part of the challenge. I want you to try and be able to start to visualize these things on your own, start to know the mental images on your own. And that's going to conclude sections 1.7 and 1.8, which are both about vectors. And in the next video, we're going to be talking about unit vectors in section 1.9, and we're going to finish off chapter 1 by discussing products of vectors in section 1.10. So I hope you had a great time, and I will see you later.